I hope, I think all of you have seen, okay, uh, assignment 1 questions which were uploaded in Moodle. Could you see them or not? Could you see that assignment?
Yes, sir.
Okay, yeah.
Yes, sir.
Okay, so all the details are given in that, okay, Moodle, okay, assignment folder. You need to upload, okay, as before the due date, okay, due time, okay, due date and due time as much on or before the due date. Okay, so I have given enough time because by keeping in mind that we have a midterm examination for some of the courses. Okay, so you need to upload, okay, them. Okay, just start working on that assignment. It's a small assignment. Okay, it's a 5 marks assignment. You need to practice some of those things because, okay, very much important. Strain hardening rate and Hall fetch relationship, slow, okay, and some numerical problem at given. Okay, so finish that one, upload it before the due date. Okay. So let me, I think, yeah, share my presentation slides, entire screen. I presume that all of you are able to see my slide number 1 for today's lecture. Are you able to see
Yes,
my
sir.
slide or not? Okay, fine, that's great. Okay. So basically, I think in my previous lecture, okay, we had discussion about yield point phenomenon, okay, which is actually one of the important, okay, one of the important phenomenon that takes place, okay, most of the times in low carbon steels, and sometimes people also observe this kind of phenomenon in other materials also, but the prominence of yield point phenomenon, like what we are talking about, okay, there will be up, okay, rise, stress is going to increase, okay, during elastic deformation. After certain amount of stress, okay, it's going to drop, okay, followed by some kind of slight serrations in flow behavior, okay, with some amount of strain. Then again it's going to continue the regular trajectory, regular path of a plastic deformation region of a curve. Okay. So this kind of thing, okay, drop in yield stress, okay, there is a yield stress, that's called upper yield stress, followed by drop in yield stress, and almost maintain, okay, almost nearly constant, okay, yield stress, that's called lower yield stress with slight serrations in the, okay, stress time curve, followed by, okay, what we are seeing, okay, non-linear path of a plastic deformation region of a material. So this phenomenon quite commonly observed, okay, in many of the low carbon steels. Okay, so this is a, that is basically related to, okay, interstitial or solute atom interaction, basically solute atom interaction, especially in steels. We are talking about carbon, nitrogen, which are basically interstitial solute atoms. Those can interact with dislocations. When they interact with dislocations, those solute atoms form, okay, a atmosphere is basically locking the dislocations, so that actually the mobile dislocation is going to be controlled. The dislocation will not able to move very easily, okay, under certain combination of strain rate, temperature combinations. Okay, so when you deform a material, okay, this locking of dislocations, okay, with the solute atoms create an atmosphere. That atmosphere is called quadral atmosphere. Okay. After certain amount of deformation, okay, dislocation can get pinned, okay, cannot be pinned, can be unpinned from the solute atoms, or solute atoms can be unpinned. Any one of them can happen depending on temperature and strain rate combination what you are giving. One of them is going to get, basically the atmosphere is going to be disturbed. So once the atmosphere got disturbed, then again it follows a regular deformation behavior. Okay, so the drop in yield stress, okay, what we are talking about, okay, this has been explained, okay, I think, okay, this has been explained by Gilman. Okay, I think the kind of theory, I think this, all these things we discussed, I'll come back to that. So this, okay, Johnston Gilman, okay, they proposed, okay, why there is a drop in, okay, stress of a material, stress of a material during initial deformation of a material. So this has been explained based on, okay, dislocation density, okay, the increasing number of mobile dislocations, and a direct relation between stress and velocity of the dislocations exist. So that can lead to drop in um, yield stress of a material. Okay, and the constant deformation is basically related to loader bands movement. Loader bands are going to get initiated at the stress concentrated region, especially near the fillet radius, radius of curvature, what you are seeing in the specimen. So that bands can propagate in one direction. So the propagation, the and initiation and propagation of these loader bands can be complex phenomena also sometimes. As a result, we do see slight serrations in the lower yield point stress. The stress what you are seeing at lower yield point, there will be some serrations because of depending on number of loader bands those are being created and propagating intersection of those bands can give that kind of serrations in the stress strain curve at the lower yield point. Okay, so basically yield point phenomena, what we are talking about, the loader bands usually creates at 45 degrees to 70 degrees. Okay, the bands can be single bands, or sometimes multiple bands, or complex bands also can form. Okay, so as far as as people have developed how this material is going to behave as a function of temperature, strain rate. Okay, and what you are talking about, the stress state, okay, at the loader band's fronts is basically not just a pure shear deformation. It also has a certain amount of perpendicular deformation. There will be another normal stress to the loader band front. So this is a complex state of stress also is going to exist at the loader band front. So all these things what we had discussion about, yield point phenomenon. So the problem with the yield point phenomenon, what we are talking about, stretcher strain marks are going to form. Okay, this stretcher strain, basically related to loader bands. Okay, loader bands formation. Okay, this can give rise stretcher strains. These stretcher strains can lead to roughness, surface roughness of the sheet. So when you use that sheet, or when you when you forming the sheet with after annealing, what happens? This undergoes loader band formation. Loader bands are going to get created. That can lead to stretcher strains. That leave a roughness of the component that has been formed out of the sheet. So that rough surface is a problematic because fatigue behavior is going to fatigue property. What you are talking about, resistance to fatigue is going to be low when you have a surface roughness. At the same time, corrosion property also is going to get affected. So corrosion is going to be higher whenever there is a roughness in the surface of the material. So these are the problems what we do see with the yield point phenomenon. Okay, this is one of the plastic instability. Okay, yield point phenomenon is one of the plastic instability kind of phenomenon what we see in materials, especially in steel, low carbon steel based materials. Okay, any doubts here? I think are there any doubts here? I think I stopped it at this slide. Okay, so we'll continue further on this aspect. So far, whatever we discussed is the yield point phenomena. If there are any doubts, please let me know. Okay. Okay. So basically, what we are talking about yield point phenomena. Okay, typically it's a schematic thing. Okay, schematically it's shown. Okay, there is upper yield stress and lower yield stress, and followed by regular plastic deformation regime. So if I deform, if I take a low carbon steel, fully annealed material, fully annealed material, if I deform it, typically I get like this kind of curve. So in order to avoid this problem of this yield point phenomenon or minimize the yield point phenomenon, people adopt two different routes. One of them using a temper rolling. Temper rolling is also called skin pass rolling, which basically involves deform the material, deform the fully annealed material, fully annealed low carbon steel. If you take that material and deform it by rolling, cold rolling. By cold rolling, about 1 to 2% of reduction, maximum 2% of reduction. Okay, that basically ends here somewhere here. Okay, the 2% of the amount of strain what you are seeing. Okay, it's about up to this lower yield point end is about 2%. Okay, depending on material to material composition, carbon content or nitrogen content, we do see the amount can vary from 1 to 2%. So what you have to do, you have to deform the sheet, fully annealed material, about up to 2% of reduction, fold reduction. that can minimize the roughness problem what we can see in the formed component. Okay, after annealing, one has to go for skin pass rolling. So this skin pass material will have numerous will have numerous loader band formation. Okay, and these are going to be this very small inside. Numerous, when you form lot of bands form, the size is going to be smaller. Okay, so when you could form the component eventually out of this sheet, okay, which was skin passed, so the effect of surface roughness is going to be much less. Okay, okay. So that way actually people try to avoid minimize the this stretch strain marks in the former components. The another approach, okay, during processing itself, during steel making itself, people add some carbide and nitride forming elements like a titanium, boron kind of things, which basically controls the controls the carbon, the free solute atoms, interstitial solute atoms, by combining with the solute atoms with forming precipitates, so that can minimize the atmosphere, quarter atmosphere. If there is not much quarter atmosphere, we don't see this yield point phenomenon in the material. These two approaches are being used to control the yield point phenomenon in a material, so that we can have a better product out of the low carbon steel sheets. Okay, so this one example, okay, here I think I'm just going to talk about strain aging. Okay. So if you look at here, assume that after temper rolling, okay, if I heat it, do some heat treatments, okay, at 100 degrees Celsius to 343 degrees Celsius, okay, heat treatments. If I deform the material, okay, we do see reappearance of okay, this yield point phenomenon. Okay, so this is called, that means actually we are subjecting to some treatment. It's called like a aging treatment. Okay, when you do aging treatment after temper rolling, okay, if I do some aging treatment, that can lead to reappearance of yield point phenomenon. Okay. Apart from reappearance of yield point phenomenon, so the yield stress is also slightly going to increase. Okay, then after that follows regular plastic deformation behavior of the material. Okay, so this kind of reappear the aging treatment again. Okay, though after temper rolling, initially we tried to what we have done, we have created atmosphere has been created fully. Okay. So we don't see that initial upper yield point. It's a smooth nice nonlinear deformation behavior. So but once you give some heat treatment, that means you are actually allowing diffusion to take place. Diffusion to take place. So during heat treatment, okay, what we see, okay, again the dislocations are going to get pinned. Okay, dislocations are going to get pinned or unpinned, can happen. So whenever we have a free dislocations and free solute atoms, those can again interact each other. So that can lead to reappearance of this yield point phenomenon. Okay, so one can explain the strain aging phenomenon like this. Okay, so assume that I deformed a material which is a fully annealed material, low carbon steel. Assume that low carbon steel which has some amount of small amount of carbon. If I deform material, fully annealed material, we can see like this behavior, stress strain behavior. Okay, now assume that now I unloaded this stress strain curve. I unloaded the stress strain. Okay, I unloaded, I remove the stress from the specimen. Okay, so if I reload it immediately, typically, when you reload it like this, it will not show formation of this yield point phenomenon. However, instead of after unloading, I do not reload it immediately. I hold it at room temperature, at certain temperature for certain amount of time. Okay, what happens? Again, we do see reappearance of yield point phenomenon, and there is a rise in stress. The yield stress of a material is going to be raised. At the same time, reappearance of yield point phenomenon is going to take place in the material. So this whole phenomenon is typically called static strain aging phenomenon. Static strain aging phenomenon in the material. Okay. So is it clear what I'm talking about? The same thing, it's in different schematic is slightly different. Okay. So okay, if you reload it immediately after initial yield point phenomenon, okay, small amount of plastic deformation has taken place. If I reload it immediately, I don't see yield point phenomenon. However, if I hold the specimen after unloading, if I hold it for a long time, okay, at a certain temperature, that can lead to reappearance of the yield point phenomenon. Okay. At the same time, the yield stress of material is going to increase. Okay, this whole concept is called static strain aging, or simply called strain aging phenomenon. Okay, that can take place in certain materials like low carbon steels. Okay, is it clear what I'm talking about? Strain aging.
So why does this happen?
Yeah. Now I want to have interaction with interactive session with this on this point. Okay, there are 2 points. One actually, upon holding it, okay, after unloading, if you hold it for a long time, if you reload it, there are two things happening: reappearance and increase in yield stress of a material. Why should, because first one actually, why first of all, why are not seeing, why are not seeing, if you reload it immediately, why are not seeing yield point phenomenon? Because already we passed it through. We passed through that, first one. If you reload it again, already dislocations which have been, now, it's now unpinned, then we are not seeing, dislocation moving at its own. We already a lot of dislocation has been generated that lead to a, directly, continuous plastic deformation. Okay, if I unload it and hold it for some time, what happens? Okay, we are basically, these are what you're talking about, carbon, nitrogen, solute atoms, which actually can diffuse easily even at room temperature. The diffusion can take place very easily even at low temperatures. Okay, so we are allowing, again, solutes to interact with dislocations. Okay, so that aging treatment, what we are trying to see again, the dislocations are now, some of the dislocations are free down, okay, and some of the, we are, after deformation, we have a lot of, dislocations, lot of dislocations already there, okay, because some amount of plastic has taken place. So the increase in dislocation density, and we are giving aging treatment. That means we are allowing at room temperature, even at room temperature also, we will see aging kind of treatment is going to take place. Okay. So dislocations, and solute atoms, dislocations cannot move very at room temperature, but solute atoms, these are carbon, nitrogen can, migrate or move very easily. Okay, so during aging treatment, we may see some of the solute atoms can interact with the dislocations, or some of them will be freed down. When you reload it again, now it's like a fresh sample, look like a fresh sample. Okay, so as a result, what we are going to see again, what you see, the solutes again can interact with the dislocations. So that can gives rise reappearance of the yield point phenomenon. So why should there be increase in stress? Why should there be increase in yield stress? Because your upper yield stress is increasing after aging treatment.
To unpin the
So
dislocation, we have to give more stress.
We have to apply
More
more
stress.
stress. Yes. Okay. So during aging treatment, what happened? Solutes are actually interacting already with the dislocations at aging, during aging. Okay. That means whatever, all the most of the dislocations are got already pinned by the solute atoms. Okay, so now I need to apply, more and more stress to unpin the, okay unpin the solute atoms. That's one thing. The other thing, we already work hardened, we already work hardened the material beyond the yield, beyond the yield point. That means already more dislocation density already have been generated. Okay, this already some cold working has been done. Okay, we are deforming material room temperature steel. If I take a steel, I'm deforming material up to around, beyond this yield point. That is already gone some amount of, plastic deformation. That means you already induced significant amount of dislocation density. Okay, even 1% of strain can give rise, around 1,000 times. Okay, this was going to get generated initially. Okay, even small amount of strain is good enough to increase the dislocation density rapidly initially. So the increase in dislocation density, okay, and the stress required to, because we are talking about the same amount of solute atoms. There's no change in solute atoms. Okay, so these solute atoms, okay, one during aging interact. Okay, that basically requires a use some upper yield stress. But the further increased stress basically related to increased dislocation density. Okay, so that's what, okay, increase in upper yield stress and reappearance of the yield point phenomenon. Is it clear? The concepts, okay, behind this strain aging phenomenon.
Sir, I still didn't get the effect of time. If you hold
Effect
it
of time.
for
They
some
say
time,
what happened during deformation. Okay, so dislocations, okay, can move, okay, very fast. Okay, solute atoms can be unpinned. Okay, now completely unpinned. Okay, now so dislocations move at a very fast rate during deformation. Solute atoms may not diffuse that much same rate. Okay, so now we have more and more dislocation density has been generated, but solids are sitting randomly. Okay, we are not seeing, okay, atmosphere is now completely gone, now it's not there that much. So during aging treatment, during aging, if you hold it for a long time at room temperature, dislocations are stopped. Okay, because we already created some dislocations, dislocation will not move, but solute atoms can migrate, can diffuse to the dislocations. Okay, so that again, what you are seeing, solute atoms going to interact with the dislocation during aging time. Okay, those basically lock the dislocations. Okay,
understood, sir.
so now again, when you deform the material, you have to unlock, okay, those dislocations. So you have to unlock the dislocations for the solute atoms. You need to give more and more stress. Okay, this that upper yield stress basically related to unlocking the, okay, unlocking the solute atoms from the dislocations. Okay, why there's increase? Okay, because the upper yield itself is basically unlocking the dislocations, okay, from the solute atoms. But there is a further increase in yield stress because of, okay, some amount of work hardening has taken place. So already we induce some amount of dislocation density. As a result, we do see, okay, dislocation itself, additional dislocation density itself can contribute to higher yield stress of the material. Then again, the drop basically again is related to, okay, Gilman-Johnston equation. You can, same thing can be used. Okay, unlocking happened. Okay, now what you see, loader bands are going to again form. Okay, okay, there will be slight interaction can take place between solutes and, okay, dislocations, but with more and more deformation at a strain rate. Okay, to attain that same external strain rate, local internally also you have to adjust the strain rate. After that, we do see regular, okay, work hardening behavior of the material. Okay, then we are not talking about interaction. Okay, solutes, the solutes actually will not, okay, migrate that much easily at during deformation. Okay, only dislocation, we are generating more and more dislocations, then dislocation can move, mobile dislocation can move at a certain velocity. Okay, depending on the strain rate what we are giving. Accordingly, we do see regular work hardening behavior of the material. Any doubts here? Any more doubts? Any more doubts here?
Sir, in case number 2,
Mm.
we are not giving enough time to that solute atom spin the dislocation. Is
Yes.
this correct, sir?
Yes, you are right. That's reloading immediately. Reloading immediately. Okay.
Sir, then the
Uh,
second case also there is a lot of dislocation, sir. Second case
yes.
also loss of dislocation density, but there
Yes.
is no little bit increase on that yield stress. The same thing will follow.
No, what you're talking upper yield stress, there's
Yes,
increase.
sir.
Okay, as compared to same material. Okay, it's supposed to be somewhere here. Okay,
No, sir.
but
Actually, I am asking in case number 2.
yes,
Actually, in case number 3, you are explaining about the dislocation density is increasing as well
yes,
as the pinning of solute atoms in dislocation. These two
yes,
phenomena are happened. But in
yes,
case number 2, there is no pinning of pinning of solute atoms in dislocation. But
yes,
already there is a dislocation is there because
yes.
we are done the experiment up to that yield
Beyond yield. Okay.
beyond yield.
Yes, yes.
So then the dislocation density may beyond certain level it may increase or
Already
otherwise it,
that stress is here. Okay, that stress is already here. the previous one, unloading, before unloading, okay, whatever is stress is basically related to dislocate density. Am I right? Before unloading, okay, this is unload before unloading thing. Okay, why are you
Okay.
getting this work hardening? Because of dislocation density.
Dislocation density increase.
Okay, the same amount of dislocation density is there now. Okay,
Okay, sir.
okay, then we are not seeing any increase in, okay, because it's following, okay, where we left the material again, it's for continually again we are going to see further increasing strain hardening rate. Okay, strain hardening, okay, is going to again happen because of increased dislocation density, further deformation.
Sir, in case number 2, if you stop the experiment again after yielding, then we cool it to some period. Then if we conduct the experiment once again, whether the yield stress will increase, sir?
No, yield stress will not increase, okay, because already we are, okay, already stress has been increased here. The same stress is going to see the little bit, okay, not much, okay. There will be slight. If you
Okay,
look at here, it's okay, very slight change will be there. If you reload it immediately, we don't see any significant change in the yield stress of material. Only in case of, okay, whenever there is yield point phenomenon is going to be seen. Okay, what you are talking about, depending how much stress you are talking about, okay, how much stress you deformed it. If okay, at what point you are unloading it, accordingly we do a slight change. Okay,
Okay,
here
sir.
actually soon after little bit of, okay, some amount of deformation you are unloading it. Okay, so usually, yeah, you are right. If we talk about cold working, okay, that strengthening mechanisms, okay, so cold working is one of the ways to strengthen the material.
Better.
That requires significant amount of, okay, strain.
Okay, sir.
Okay, then yeah, there is increase in stress. Okay, that's called cold work strengthening. Okay,
Okay, sir.
mechanism. Here, what you are talking about is just a little bit. Okay, so we do see small change is going to happen here because we are talking only small, less than around 2-3% only. What you are talking about 40-50% or 80% deformation. Okay, if we go beyond 40% deformation, then we do see significant increase in the yield stress of material. Okay, here just we are talking about just around 3% of strain. Okay, here assume this is about 1 to 2%. Then after that we define 1 more% extra strain. Then we unload it. Okay, 1% extra deformation has been given. So this basically what happens. Okay, we are giving enough time. Okay, so during static time, okay, not only this extra dislocation density, okay, even, okay, more and more solute atoms, okay, yeah, maybe available. Assume that there's some more solutes are available than the now dislocation density, initial dislocation density. Okay, initial dislocation density, assume that very small amount of dislocation density is there, but you have enough solute atoms more than the, okay, required thing. So we need only how much we said 0.04, okay, 0.04% carbon is good enough, okay, to fully anneal the material. Now what happened after some amount of deformation, your dislocation density has been increased, but at the same time you have some more solute atoms are interacting. Okay, that can give us, okay, one actually additional increased dislocation density, and we also have some additional free solute atoms. Okay, that can again pin the additional dislocation density. That's why we are seeing upper yield, okay, increase in upper yield stress. Is it clear? I think it's a little bit, okay. Do not get confused. Okay. Now
Okay, sir.
we already had seen the discussion, okay, earlier in the previous lecture. We need only, okay, for example, we take a fully annealed material, okay, we need very small amount of, okay, solute atoms. Very small amount of solute atoms are required to pin all the dislocations. Okay, that is okay. Even if you take fully cold material, also only talk about 0.04%. But if it already I showed two examples, okay, fully annealed material and fully cold work material. Okay, in both the cases, the order is going to change. The amount of, okay, solute atoms required. Now assume that the low carbon steel, which has about 0.1% carbon. Okay, assume that we have a 0.1% carbon steel. That was initial material. When I, okay, fully annealed material about 10^6 to 10^8 centimeter square dislocation density we have. Okay, so that requires only very small 0.0, assume the 0.04%, okay, required, but you have some more carbon atoms already left out, free atoms, okay, solute atoms are still there after pinning all the, okay, dislocations which are present in the fully annealed material. Now during deformation we are generating some additional dislocations. At the same time we have, okay, some extra carbon atoms, those also going to pin the additional dislocations. So as a result, okay, we are going to see increase in upper yield stress of the material. Is it clear, Saktiver? I think now,
Yes, sir. It is clear, sir.
okay. because we have so much, okay, we have more solid atoms than the, okay, required for pinning the complete dislocations always, okay.
Okay, sir.
Okay, so when you deform material, more and more dislocation generating, at the same time more solids will come into, okay, interact with the additional dislocations. Now actually we have more carbon, if you assume the carbon atom is forming, now actually the atmosphere is more, okay, entire the volume fraction atmosphere is going to increase. That requires more stress to unpin the completely, to unpin the dislocations of the solute atoms. Okay, I hope it's clear to all of you about the static strainaging. So one can, okay, estimate what is the fraction of, okay, solutes segregating to the dislocations. Okay, so Cottrell and Bilby, basically the same people, okay, who explained yield point phenomenon. It basically it's following, okay, same thing. Control, they continue explaining this strainaging, okay, about, okay, how the dislocations are getting, okay, pinned by solute atoms. So one can calculate what is the fraction of solutes, okay, segregated to the dislocations in a time t. Okay, we are talking about aging, okay, time. Okay, this aging can happen at room temperature, can also keep it 100 degrees Celsius, can have keep it up to 200 degrees Celsius, like that. So depending on temperature, the time required, okay, for the solutes segregation, okay, is basically it's a time temperature dependent phenomenon. Time temperature dependent phenomenon. So at a given temperature, the time, okay, in a given time t, okay, how much fraction of solutes can segregate to the dislocations. Okay, they are given the fraction of solutes can be estimated by using, okay, this equation where, okay, d is the diffusivity, okay, diffusivity of the solutes, and, okay, this is a constant, so k is a constant, okay, alpha is a numerical, rho is the dislocation density, okay, so t is the temperature, okay. So this equation has been proposed, okay, to understand, okay, how much fraction of solutes are segregating to the dislocations in a given time t at a given temperature t. T is small t is the time, capital T is the temperature, and temperature will also be part. Okay, diffusion will have a temperature d is equal to d naught exponential minus q by RT. So the temperature effect and time effect has been taken into consideration to understand, to estimate the fraction of solute atoms. Okay. So this equation was found to be valid. It's found to be valid when the time is short. Okay, when the time is short. Okay. If the time is longer, okay, people figured out this equation might not be hold true. Okay. So the another, okay, person, Harper, he has proposed slightly different equation, okay, a better equation for longer aging times, okay, because at low room temperature one has to hold it for long time, so many months, okay, then only we do see reappearance of the yield point phenomenon, okay. So for such long times, okay, we cannot use this, okay, whatever Cottrell Bilby has proposed. So Harper equation is well, okay, found to be well, okay, equation which can be used to, okay, find out what is the fraction of solutes that can segregate to the dislocations in a given time and temperature. It's added exponential, okay. So here it's the same time. See, this is the kind of, okay, power law kind of thing, 2 by 3, okay, power. Here he has given an exponential kind of equation, okay. So this has been, okay, found to be, okay, true in, for example, okay, they taken a niobium specimens with oxygen atoms. Okay, niobium is also BCC material like AFC, like iron, niobium with some, okay, interstitial atoms, oxygen atoms, and they, okay, they could, okay, see that how, okay, as a function of time, fraction of solutes, okay, which okay, which interacted with the dislocation, segregated to the dislocations. When they figured out short times, okay, this, okay, Cottrell Bilby equation was found to be, okay, valid only for short times. So when it comes to long times, okay, this equation failed. So but if you use Harper equation, people found that this equation found to be better suited than the Cottrell Bilby equation, okay, to estimate how many number of, okay, solutes are getting segregated to the dislocation for a given dislocation density material at a given time and temperature, okay. So this is about the strainaging, a static strainaging phenomenon, what we see in materials. Okay, steel is one of the best examples, and also, for example, here another example, niobium with, okay, oxygen atoms. So interstitial atoms, okay, play significant role, okay, in yield point phenomenon. Okay, So the reappearance of yield bond phenomenon and increased upper yield stress, that phenomena can happen when we hold the material after some amount of deformation. So that is called strain aging phenomenon of a material. So any doubts here? I think. Are there any doubts? No? Okay, we'll move on to some extended thing. Okay, what we're talking about static straining, what we talked about is static strainage. We also see dynamic strainage. Dynamic strainaging. Okay, the name itself indicates, okay, if strainaging happens, that means actually the aging happens during deformation. During deformation. So that is called dynamic strainaging. Okay, so this is another important phenomenon which we see in many materials. Okay, many materials we do see this kind of dynamic strainaging phenomenon. Here I'm talking about two different materials. Okay, here for example, okay, titanium, okay, with some amount of atoms, okay, oxygen atoms or yttrium. Okay, so what they people observed when these materials, okay, this titanium alloy, titanium, okay, with small amount of oxygen or yttrium, what people have observed when you deform material as a function of temperature, as a function of temperature, okay, we usually anticipate, okay, the stress usually supposed to decrease with temperature, because thermal activation process are going to happen, cross slip, those things are going to take place during plastic deformation. So with increasing temperature, as a result, one can expect the stress of a material, okay, the flow stress of a material, strength of flow strength or a tensile strength of a material is supposed to decrease with decreasing temperature. However, in these materials, what people have observed, okay, there is a initially decreased, afterwards in a certain temperature window. In a certain temperature window, okay, there was a slight plateau or some peak. Okay, some peak in stress has been observed. Okay, so instead of continuous decrease in strength of a material, so there is a plateau. That means in a certain window of temperature, okay, people have observed, noted that there's some kind of, okay, plateau in flow stress or some peak in a flow stress has been observed. This is one kind of material. Okay. So in another kind of material, if we talk about super alloys, in Cornell 600 kind of alloy, okay, yield stress, okay, continues almost decreased. Okay, however, the ultimate tensile strength, okay, is increased, okay, in certain temperature window. Okay. So so this is basically anomaly, okay, in a regular what we expect, okay, continuous decrease. We are seeing anomaly in a flow behavior of the material. Okay, so this kind of things were attributed to a phenomenon called dynamic strainaging. Okay, so Lee Chatelier is one scientist, okay, around 1902 or 1903. He was the first one who was reported in mild steel, in mild steel, when it was deformed in a temperature range, okay, around, okay, 100 degrees Celsius to, okay, in a temperature range of 100 degrees Celsius to 350 degrees Celsius temperature range. Deformation test temperature, deformation test temperature 100 to 350 degrees Celsius. He observed an increase in yield stress of a increase in stress, okay, the strength of a material or yield stress both have been increased, okay, rather than decrease with increasing temperature. So that was the first, at the first time, okay, an increased yield stress or increase in flow strength of a material with temperature has been reported by Lee Chatelier. After that, okay, Portwin Lee Chatelier around 1912, okay, he also observed in certain class of materials, okay, aluminum alloys. Okay, so the Portwin is another one, another scientist who also reported, okay, this kind of increase in yield flow strength of a material with temperature rather than decrease. So this has been observed not only in a interstitial solid solution, it also observed in substitutional solid solution alloys. Okay, so this thing has been attributed to dynamic strainaging. I hope many of you know about blue brittleness in steels. I hope, okay, blue brittleness in steels. Any idea? Anybody has idea about blue brittleness?
Yes, sir. During that warm rolling of the material, we can see that blue brittleness.
Yes, okay. Basically what happens, the fracture strength is going to increase, it becomes brittle in nature, okay. Ductility is going to come down. The fracture strength, okay, the strength, what you are talking about, the strength of material increase during in warm rolling, okay, when you do at a certain temperature range, 100 to 350 degrees Celsius, okay, depending on rate of deformation, okay, that temperature can shift towards right with increasing strain rate, the temperature is going to shift towards right, okay. It can increase, okay, 350 up to around 550 degrees Celsius also, okay. From 300 to 550 degrees Celsius also can happen, okay. So the temperature window, okay, is going to shift the increasing strain rate, okay. Under quasi-static conditions, okay, if you deform a steel, okay, if you deform a steel in a temperature window, okay, between 300 to 550 degrees Celsius, people observe, okay, material becomes brittle in nature. So that is called blue brittleness. The word blue has come into picture because of surface appearance. Okay, when you heat the material, the steel material, when you heat the steel around that temperature, so there's some oxide is going to form. That oxide, okay, gives, okay, the surface of, okay, the surface of the material becomes a blue in color. That's why they call blue brittleness. Okay, that's nothing but dynamic strain aging phenomenon, okay, which can take place when you deform a material in certain temperature window at a particular strain rate window. Okay, so this is concept is called, because during deformation, if there is a strain aging phenomena taking place, that phenomenon is called dynamic strain aging phenomenon. So what are the okay, manifestations of the dynamic strain aging? One we already discussed, flow stress can, okay, can become plateau, or can we see some peak in the material, okay, in a certain temperature window. That's one thing, okay. Ductility is going to come down, okay. Ductility is going to come down in this okay, in this temperature window. That's another manifestation, okay, of a dynamic strain aging. Okay, during this treat, okay, whenever there is a strain aging taking place during deformation, okay, work hardening rate is going to increase. Work hardening rate, the theta, okay, d sigma by d epsilon is going to increase in this temperature window, okay. Apart from these three things, okay, we also know that Hall pitch, okay, we talk about yield stress of a material. Yield stress also, some materials yield stress is going to increase, some materials, okay. So that yield stress we are talking about, okay, or flow, even if you take a flow stress in terms of a grain size effect, okay, the Hall pitch coefficient slope, KHP, okay, the K is also going to increase in this temperature window, because we already said the K is basically indicates the dislocation locking parameter. Okay, during when you deform material in this particular temperature window, okay, solute atoms are going to interact with the dislocations that basically increase the strength of a material, okay. So your Hall pitch coefficient also going to increase, okay. That's another manifestation of a dynamic strain aging. Apart from these things, okay, there's another important thing called, okay, negative strain rate sensitivity. Negative strain rate sensitivity. So strain rate sensitivity is M, okay. We know that sigma is, typically we say sigma is proportional to strain rate power of M, okay. So the M, okay, typically we expect for most of materials positive, okay, but certain materials which exhibit this dynamic strain aging, okay, those materials can exhibit negative strain rate sensitivity. This is another, okay, important manifestation of dynamic strain aging. The most other important, some materials will also show serrations, okay, some kind of serrations in stress strain curves. The stress strain curves will be having certain serrations when you deform a material in this temperature range, okay. We do see serrations are going to form in the stress strain curves. So the same thing, or whatever I mentioned, those things have been summarized in a, okay, in this form, okay, as schematically. So the temperature effect, we assume that, okay, it's already fixed some strain rate, okay. In that particular strain rate window, if you deform material, okay, as a function of temperature, the strength of a material is going to decrease initially, but in this window, in the particular temperature window, okay, stress can increase or can become plateau also, okay. Apart from that, we also see strain hardening rate is going to increase, and Hall pitch coefficient K, okay, the dislocation locking parameters are going to increase slightly in the in this temperature window, and we also see ductility is going to be minimum. Okay, ductility can be seen minimum in this material, and we also see negative strain rate sensitivity. Negative here slightly people use different gamma. It's okay. It's close to m. Okay, it comes very close to m. Okay, but nevertheless, if we determine strain rate sensitive material, we do see negative in this window. Apart from that, we do see some serrations. We do see some serrations in stress strain curve of the material. Okay, so I think that listed down all these important manifestations of dynamic strainaging phenomena. Okay, is it clear about dynamic strainaging?
So the yield point phenomenon will also be seen, right? In this, the upper yield point and the lower yield point thing will
It's
also be
basically,
seen.
yeah, because when during deformation itself, we are seeing such kind of phenomena. Okay, the interaction happened because we are giving. Okay, I'm said in a particular temperature window, or strain rate window, whatever. Okay, in that window only we do see. Okay, even if you take material, some material which has a solute atoms, it can be interstitial or substitutional. Depending on type of solute atoms, we do see the temperature window. In the particular temperature window, there is a interaction of the these two can take place. So that can lead to this kind of phenomenon. I think the same thing here. I think here intermediate strain rates and temperatures lead to a competition between one. Usually with increasing temperature, typically we expect there will be thermal activation, climb, cross slip, those can happen very easily. So that should usually lead to decrease in flow strength of a material. Okay, however, at with increasing strain rate, shortens the time available for diffusion of solute atoms, thus weakens the obstacle, leading to decrease in strength. Okay, so these two, between what we are talking about, there is a competition between thermal activation and aging treatment. Competition between thermal activation and aging treatment. Okay, so that can gives us some window. Okay, that can happen only in a particular window, of strain rate and temperature. Okay, so schematically the same thing was explained like this. Okay, if you talk about stress, if you talk about the strain rate is in opposite direction. Okay, here, strain rate increasing with increasing. Okay, your stress basically combination of activation, thermal activation, due to thermal activation and aging. Okay, so the aging is basically combination of concentration of solute atoms, diffusion and time. Diffusion and time. Okay, so opposite of strain rate basically time. Okay, because strain rate is basically 1 by t. Okay, time 1 by, you're talking about per second. Okay, so strain rate can also be opposite to time. So it's basically increasing time or decreasing strain rate. Okay, in this way, it's increasing time or decreasing strain rate. So when you have with the we are giving enough time. When there is a enough time, we can see some due to aging. Okay, we are basically facilitating more interaction of the solute atoms with the dislocations. That can lead to aging of the material. Okay, so with the time, at same temperature, hold it at same temperature with time. Okay, we do see thermal activation. Okay, happens that usually brings down the stress of a material. So in a particular window, aging is going to dominate. Okay, than the thermal activation. Okay, as a result, it may dominate or become equal. Okay, if it become equal, then we do see plateau. Okay, in a stress strain curve, in actual overall stress strain curve. If you talk about the stress is going to be constant. Okay, if aging dominates than the thermal activation, then the stress is going to increase. Okay, so this is a kind of interesting observation people have made. Okay, it is something to do dynamically. Some aging treatment taking place is nothing but interaction of the solutes with the dislocation taking place. That can that strength can contribute to your overall stress of a material. Okay, so depending on temperature and strain rate combination, we may see the strength contribution from aging can be significant to drop in activation. So in that case, we do see the stress can become plateau or can also increase if the aging is dominating the stress. Okay, So another way of people have explained, okay, another way, okay, what people have done, okay, this is basically your, okay, stress as a function of, okay, velocity, this, okay, dislocation velocity, okay, dislocation velocity is going to increase with increasing, okay, strain, the rate of deformation, with increased rate of deformation, your dislocation velocity can be expected to increase according to Borowan equation, okay, strain rate is equal to rho BV, rho BV. Okay, with increasing strain rate, one can expect there is increase in, okay, dislocation velocity. Okay, so what happens with increasing strain rate? With increasing strain rate, okay, the stress is going to increase. The stress is going to increase. Okay, but if we talk about if there is a solute, okay, if there is a solute, okay, we are going to see some drag effect. That means we are trying to stop the dislocation velocity, control the dislocation velocity. Okay, in that case, what happens? Okay, the stress is going to rise. Okay, in a particular strain rate window, in a particular strain rate, that means particular. Okay, this velocity can depend on strain rate and temperature also. We are talking about, for example, only strain rate. We do see, okay, in particular window, okay, we do see the drag effect, solute drag effect on the dislocations, okay, can dominate. Okay, that can also increase the strength of a material. Okay, so this is where actually people have explained, okay, dynamic strainaging in materials. Any doubts here? It's a kind of mechanism which basically tells about how strength of a material can become equal or can be higher in a particular temperature strain rate window. Any doubts here? It's basically interaction, nothing but, okay, it's solute atoms interact with the dislocations during deformation itself. Is it clear?
Sir, that TW on the graph, the
Mm-hmm.
x-axis, is it time or temperature?
No, it's a time. It's a T is a time. Okay. Here we're talking about strain rate or time. Okay. In this direction, strain rate, it's the same. It's the same. I'll tell you. Okay. If you talk about, okay, opposite direction. Okay. This is basically with increasing strain rate. It's basically increasing strain rate. Dislocation velocity is going to increase. Okay. Your stress is going to increase. Okay. Similarly, with increasing, okay, strain rate, the stress is going to increase. Okay. It's opposite. This is the one, actually, that strain rate x-axis has been changed in the opposite direction. Okay, it's a thermal activation without any, okay, solute atom interaction. The moment when the solute interaction happens, okay, we do see it's a particular, okay, time. If you give enough time, we do see enough, okay, aging can take place. That means interaction. The solutes can pin the dislocations. Once you
So,
go to high temperature, high, okay, low strain rates, okay, so we do see again the okay, thermal activation is going to dominate.
so you're giving more time and you're giving more temperature
Yes,
at the
that's
same
it.
time.
Yes, that's it's the same thing. Okay, well, let's we talk about time because I'm telling. Okay, this aging phenomenon is basically time temperature dependent phenomenon. Time temperature dependent phenomenon. Either have to increase time or increase the temperature. Okay, to have a aging. Okay, increase, okay, time means decrease the strain rate. Decrease the strain rate. Okay, it's opposite basically. Okay. So if we deform material very slowly, we are giving enough time for the solutes to interact at a given test temperature.
So if you're just increasing the time and not increasing the temperature, then there'll only be that increase in stress, right? You won't see a decrease in stress because you're not increasing the temperature,
No, no.
right?
See that we are talking at a particular temperature. Okay, that's what I said. Okay, it's always there is a window of strain rate and temperature. Okay, the combination, the strain rate and temperature combination is going to vary. If the temperature is high, okay, you can go to high strain rates a little bit. Okay. If the temperature is low, okay, we have to give low strain rates. Okay. This combination is very important. Okay. During deformation, always this is an external parameter. Okay. Strain rate and temperature external parameters. So these two combination play a role in a dynamic staining. Okay. Dynamic staining can be, okay, can be expected in a particular window of strain rate and temperature. Once you cross the temperature window, for example, if you talk about, okay, I'm talking about particular strain rate in the temperature window you are seeing. Once you cross the temperature window, okay, we are giving more diffusion to take place. That means atoms can, okay, move, diffuse very easily. Then we don't see much interaction of the, okay, dislocation moving at particular velocity. But when you increase the temperature, your dislocation solute atoms going, okay, diffuse faster than the dislocation velocity. At low temperature, okay, so below that window, okay, below that window of temperature, we are not giving enough time, okay, enough temperature diffusion to take place. So that's what, if we talk about a particular strain rate, what is the effect of temperature? At a particular temperature, what is the effect of strain rate? Okay, so the effect of strain rate basically tells about the time. Okay, when you talk about anything dynamic thing, that means we are talking about strain rate effect. Okay, is it clear? Because it clearly says that there is a particular window of strain rate and temperature. In that window only, we do see dynamic strainaging phenomenon. Once I fix my strain rate, the temperature is going to be certain window. Okay, if we increase the strain rate, my temperature window may shift to, okay, different window. Okay? The window may change. Okay? So whatever I think we have seen here, okay, these phenomena, whatever seen at a particular strain rate, the strain rate has been fixed here. If I change the strain rate, we may see some shift in the temperatures. Okay, with increasing strain rate, okay, the time has come down. That means you have to increase the temperature. Am I right? For example, now it was deformed at a particular strain rate. This all data was established at a given strain rate, 10 power minus 3 per second. Assume that. Now, if I deform material 1 per second, that means I brought down the time available. Okay, but if I want to see interaction, I have to increase the temperature. That's where actually your temperature window shifts towards right. If I increase the strain rate, if I lower the strain rate, okay, that means you're giving enough time. Even at low temperatures also, we do see enough diffusional activity. Okay, so there is always a window. It's like a CCT curve. Okay, we do see in CCT curves there is a window. Okay, temperature window. Okay, below that, above the diffusion and nucleation problem. Okay, so that's the kind of, similarly here also. Okay, what you're talking about, interaction of solutes with the dislocations play a significant role in the dynamic strainage. So how you are brought together this interaction, that makes difference. Okay, so it can be depending on the time and the temperature. The time basically we're talking about here indirectly in the form of a strain rate. Is it clear?
Yes, sir.
So because the statement is here clearly. Okay, the nature of thermal activity is such that flow strength increases with increasing strain rate. Okay? And increasing strain rate shortens the time available for diffusion of solute atoms. Thus weakens the obstacle, leading to decreasing strength. In the form, we're talking in terms of a strain rate. If you talk in terms of temperature, okay, with increasing temperature, okay, thermal activation, okay, what happens? We do see flow stress going to decrease with increasing temperature. And we are giving, okay, enough temperature that means diffusion can take place very easily. Okay, so that also basically leading to more and more, okay, interaction can take place. It's opposite. When you talk about here increasing strain rate, we are talking about, okay, fixed temperature. It's a fixed temperature. Okay, if you talk same thing, can talk in terms of, okay, fix the strain rate and change the temperature and talk about, okay, what happens. Okay, is it clear about, okay, aging treatment during deformation of a material? Okay, so this different kind of mechanism people have given, okay, to explain this dynamics, but more or less basically related to solute interaction with the moving dislocations. That's it. Okay, that can give this dynamic strainaging phenomenon in the materials. Okay, this is also another plastic instability. Okay, because there should not be sudden increase. Okay, because that basically does a lot of problems during working. Okay, the material. The blue brittleness, one of the things, which is one best example, which come under the category of dynamic strainaging phenomenon. Okay, this is basically what we discussed about one phenomenon. Okay, the explanation basically related to, okay, why do you see a plateau in stress or increase in, okay, stress, okay, during the dynamic strainaging phenomenon. Okay, next one. Okay, we also said there will be negative strain rate sensitivity. There will be negative strain rate sensitivity in the material. So we know that, okay, we already discussed stress typically taken as a function of strain at a given strain and temperature. At a given strain and temperature, okay, sigma is equal to strain rate power of m. This m can be, okay, typically, okay, most of the materials, okay, which do not exhibit dynamic strainaging, m value will be positive. 0 to, okay, can vary up to 1. 0 to 1. If the material shows, okay, okay, if material shows dynamic strain energy phenomenon, that means actually M can be negative. M value can be negative in nature. So we know that if it is a positive, if M is positive, okay, for example, here shows okay, how is the stress of a material, okay, our stress strain curve, if we take a stress strain curve as a function of M, okay, at room temperature, if it is a material, okay, if we just assume that a material is showing okay, like this increasing strain rate sensitivity. So if I take materials of increasing strain rate sensitivity, one can expect an increased okay, strain ductility is going to increase okay at lower temperature. Okay, even small increase in okay strain rate sensitivity M value, okay, even if you increase small strain rate sensitivity value, I do see okay people have seen some materials will exhibit an increased okay ductility in the material. Okay, even if you go to high temperatures, okay, many materials, there are materials called superplastic materials which exhibit very high strain rate sensitivity values. High strain rate M values can be very high, okay, can be about 0.3 to 0.6 we do see. Okay, those materials okay at elevated temperatures okay exhibit very large elongations, okay, 1000%. Ductility can be the percentage reduction, okay, what elongation can be as high as okay 1000%. Those are called superplastic. We will discuss separately, okay, which is basically high temperature phenomena, which can be seen, okay, where some materials exhibit very high strain rate sensitivity values. It basically tells that if the strain rate sensitivity is positive, okay, with increasing strain rate sensitivity, we do see an increased ductility. If the strain rate sensitivity becomes negative, what does it mean? Okay, with increasing temperature, with increasing strain rate, with increasing the stress is going to come down. That's called, that gives basically negative strain rate sensitivity. Negative strain rate sensitivity. What it indicates that okay, your ductility is going to come down. Okay, so we always need to have a higher strain rate sensitivity to have a increased ductility in the material. So negative strain rate can lead to reduced, okay, because what's happening? There is a plastic instability. Localized strain is going to get localized locally, okay. That can lead to premature failure of the material. So that can lead to okay minimum in the ductility in the dynamic strainaging phenomenon. Okay, that's about the negative strain rate sensitivity. And the most important thing, serrated flow behavior. Okay, serrated flow behavior. So dynamic strainaging phenomenon, okay, can also be seen as a okay presence of okay these serrations in a stress strain curve. The material can show serrations in a stress strain curve. Okay, if I zoom it, okay, we may see this kind of serrations. Okay, this is one of the manifestations of dynamic strainaging. Sorry. So can anybody give okay, so can anybody give some examples for where do you see serrations in stress strain curves? This is one example I already given. Okay, dynamic strainaging okay can show can give some serrations in stress strain curve. Are there any okay cases which can cause serrated flow behavior?
Sir, after the lower yield point, you see some kind of sedation, like
So because this is related to okay all are strainage related thing. Okay, that's one already we discussed. Okay, yeah, yield point phenomena also gives okay the serrations. That's also related to solute interactions with the dislocations. Okay, any other cases, okay, other than dynamic strainaging or strainage, okay, what you're talking about, okay, yield point phenomenon. Other than that, any other places where we can see this some kind of serrations. It cannot necessarily be of same type of serrations, but we do see some serrations in the stress strain curves or some undulations in the stress strain curves. Are there any physical process, okay, apart from, okay, this solute interaction with the dislocations? Any idea which physical process can give serrated flow behavior?
Sir, I don't know it happens stress and strain, but it occurs in machining process of titanium alloys.
Mm-hmm.
Serrated chips get formed.
Serrated
Chips.
chips.
Chipping.
Yeah, I'm talking about in the stress strain cause. Okay, we deform a material
No, sir.
plastically. Okay, during plastic deformation of a material. Okay, if it generates stress strain cause, okay, we do see some serrations. Okay, one example is already we discussed. Okay, so people have also noticed, okay, serrations not only due to dynamic strainaging, we also see some type of serrations, okay, due to, okay, one actually twinning, okay, in single crystals, okay, in single crystals when you deform a material. Just 1 minute. Somebody has joined now. Okay, so already listed. Okay, whenever, okay, this is the first one. Okay, dynamic strainaging and Portwin, okay, Portwin Lee-Chatelier effect, which basically cause, okay, serrations in the material in the stress strain cause. That's one thing. And people also observe whenever there is a mechanical twinning, deformation twinning, okay, in single crystal materials, in some polycrystal material also can give some serrations in the stress strain cause. And the other thing, whenever there is a temperature rise and drop, okay, because accordingly, whenever there's adiabatic heating in the material, like low conductive materials, when you deform, that's what, okay. If you talk about, okay, I think titanium, okay, we do see the serrated chips, okay, because of, okay, adiabatic heating. That also, if it generates stress strain curve, we get a serrations, slight serrations in the stress strain curves whenever there is a adiabatic heating. Okay, and whenever there is phase transformation, for example, if you deform a material, okay, steel, austenite, okay, okay, at some temperature we do see, okay, martensite formation, deformation induced martensite. Okay, that also during deformation, if there is any transformation, phase transformation, that can also give some serrations in the stress strain curves. Okay, even also dynamic strain, okay, recrystallization and grain growth can also give you some serrations. Some not, okay, at certain temperature combination only we do see dynamic recrystallization, grain growth can also give, okay, serrations in the stress strain curves. Okay, some examples here. I'm talking about three. Okay, here for example, it is a Portwin Lee-Chatelier effect, which has been seen quite extensively in aluminum alloys, aluminum magnesium alloys, aluminum copper lithium alloys. So people have, okay, observed, okay, when you deform material, okay, in a particular solution treated condition at room temperature, a particular strain rate. Okay, so this basically talks about effect of, okay, alloying content, okay, alloying element and alloy solute atoms. Okay, here I'm talking about only lithium, okay, and lithium plus copper, okay, and only copper. Okay, so in certain combination of alloying elements, okay, we do see the serrations can be seen in the stress strain curves of a material. Okay, so this, I think, one of my, I think, PhD students who has graduated. He had worked a lot on, okay, effect of lithium, okay, copper, okay, on this dynamic strainaging of, okay, anisotropy in the material. So I think, yeah, this is again one example. What we see dynamic strainaging, basically, Portwin Lee-Chatelier effect also is a subset of dynamic strainaging. Portwin Lee-Chatelier effect is quite commonly observed in, okay, non-ferrous metals, okay, like aluminum alloys, aluminum, copper, lithium, aluminum, magnesium alloys. Okay, the other thing, twinning, okay, single crystal, okay, some material when it was deformed, we do see, okay, this kind of, okay, serrations in the stress strain curve. And, okay, when around 0.68% carbon steel, when it was deformed at a particular strain rate, okay, we do see this kind of, okay, serrations in the stress strain curves. Okay, So even deformation twinning, okay. So deformation twinning, deformation-induced martensite, that also will give you some serrations in the stress strain house. Okay. So I think, okay. So there are three different types of, typically we do see the serrations can be of, okay, as far as dynamic strain is concerned, okay, we do see different types of serrations, A, B, C type serrations will be seen here. Okay. The A type is like a, okay, periodic. Okay, there is a periodic, okay, and some, okay, look at it, we assume that this is my stress strain curve supposed to be like this, but we do see there is an increase in stress followed by drop in the stress again, okay, follows a regular path again, okay, increase in stress and drop in stress. So this kind of, okay, periodic, okay, serrations will be seen. Okay, okay, this is basically related to, okay, locking dislocation interaction, okay, with the periodically it happens. It's called type A serrations can be seen. Type B serrations, okay, large fluctuations can be seen. Okay, discontinuous flow can happen, okay, within the deformation bands. Okay, that can happen. That can give you this type of serrations. And type C, it happens. Okay, the serrations happens below the average. Okay, below the actual stress time. It's supposed to be. Okay, this is called type C. Okay, serrations. Okay, these are basic types of serrations what we see, okay, in a Portwell-Lichat layer effect or dynamic strainaging phenomenon of a material. Okay, so localization of strain in the form of deformation bands due to inhomogeneous plastic flow can give serrations in the material. The types of serrations are going to depend on, okay, alloying elements, or okay, what is the effect of concentration of alloying elements, time, temperature, and strain rate combination. All those things can dictate what type of serrations can be formed, okay, in a stress strain cause of a material which exhibiting dynamic strainaging in the material. So people also have seen, okay, there are other, okay, apart from ABC, people also see D, E, F. Okay, there are different types of, okay, serrations have been seen in the materials. Okay, so which exhibiting dynamic strainaging in a material. Okay, so for example, stainless steel, okay, which is known to exhibit dynamic strainaging. Okay, so depending on temperature, okay, it's a pretty already fixed the strain rate and compost has been fixed. Again, we do see the type of serrations are going to change the moment when you change the temperature of the material. Okay, even within the temperature window, the type of serrations are going to change, okay, depending on temperature of the material. Okay, so the type of serrations can vary. Okay, can be A, B, C type or A with B. Okay, so for example, here initially we have a A type, then suddenly we are seeing A with in between. We are seeing a B type of serrations also. So this kind of combination can also be seen. Everything depends on, okay, the role of, okay, solute atoms or precipitates, how they're interacting with the dislocations. Okay, and depending on temperature, the temperature strain rate can play a role, okay, on the material. So my last slide, okay, basically, so the serrated flow behavior can be seen. Okay, if you talk about strain rate versus temperature, okay, 1/T temperature. Okay, so there is a window. Okay, within that window only we do see serrated flow behavior. Okay, above that window we may not see. Below that window we don't see serrations in the material. Okay, Portwell-Lichat layer effect is a subset of dynamic strainaging. Okay, so it's not so different. PLC, Portwell-Lichat also is one of the dynamic strainaging phenomenon, which is basically involves negative strain rate sensitivity. Okay, the strain rate sensitivity is a negative. In dynamic strainaging materials, some materials may not show negative strain rate, but may show, okay, strain rate sensitivity. Here actually M, okay, M is basically here S is shown is about 0. Okay, so PLC effect is always associated with a negative strain rate sensitivity. Dynamic strainaging can be having strain rate sensitivity 0 to negative values. Okay, so this is about the, okay, dynamic strainaging behavior of a phenomenon of a material. So I'll stop it here. If there are any doubts, please let me know. If there are any doubts, please let me know.
Sir, so PLC and dynamic strain aging are essentially solute effects, right? So without solute, this won't happen.
Not necessarily solute, precipitates also play a role. Okay, fine precipitates also. So there is a lot of debate, okay, whether precipitates can also give or not. Okay, so both solute atoms and precipitates interaction with the dislocations can play a role in the dynamic strainaging. With the okay, the precipitates or solutes should interact with the dislocations during deformation. most of the times people observe solutes play significant role than the precipitates.
But if you take the pure metal, the dynamic strainaging will not happen. Sir.
No. Okay, whatever you're talking, yield point phenomena, strainaging, dimension, is all are actually okay interaction of the solute atoms with the dislocations, or some fine precipitates with the dislocations also. That also plays some amount of role on the dynamic strainage. Okay. Any more doubts? Okay, if there are no doubts, okay, I think what I will do, let's move on to the okay topics. Okay, sorry, seminar term paper titles discussion. So I'll open that file. Okay, just 1 minute. Yeah. Aryan Baghani, is he there? Is he? Aryan Baghani? Okay, I'll come back to these people, okay, who have not indicated their name. Okay, some of them indicated here down the line. Okay, so first, who are indicated the teams? Okay, Madapala Govind and Sai Manos. One of you are there. Sai
Yes,
Manos.
sir.
Huh?
This
Who
is
is it?
Govind. Govind, sir.
Okay, so you need to select okay one number 1 to 14. Any one number.
Okay, sir. 14.
14. Okay. So Rubal and Somizit, select okay. Apart from leave that 14 number, you can select 1 2 to 13 now. Any one of them. Rubal, Somijit. Are you there? No. Those are there. Rubal, are you there? Okay, next one. Okay. Next one, who is that? Okay. Suman Arjun, Keshu Kumar.
Yes, sir. Suman RJ.
Yeah, can you select one of the okay 1 to 13?
4.
4. Okay. Sektivel, Praful,
Sir, 11, sir.
11. Okay. Pratik Kumar Singh is already indicated. Okay. It's already is 11 na, for you. Okay, 11. Okay, fine. Shweta, Sudha.
5, sir.
5.
Yes, sir.
Okay. Shagra Tiwari and Venkat Meher Sai got
Hello. Yes, sir. 7, sir. 7.
7. Okay. Muhammad Arif Khan. Akshay Prasad. Pranay Kumar.
Yes, sir.
Can you select one number?
9.
9. Okay, fine. Rajat Kumar. Okay. Abhijit, Deepak.
Sir, 10.
10. Okay.
10.
Okay. Monish and Ravi Shankar.
Yes, sir.
Can you select one number? Okay, already see 4, 5 over, 7 over, 9 over, 10 over, 11 over, 14 over.
2.
2. Okay. Bhargav, Manikandan,
Sir, 3.
3. Okay. Okay. Anybody else left who have not indicated their teams or single team, single person team? I think all of you given indicated your numbers, am I right? Okay, so whoever not attended, for them I'll give them random remaining things. Okay, just 1 minute. I'll share. Okay, so these are just see that. Okay, the numbers what I indicated. Okay, Madapala Govind and Sai 14. Are you able to see the Excel sheet, some spreadsheet?
Yes, sir. It is.
Yes, sir.
Yeah, just see that. Okay, Rubal he did not. Suman Arju. Okay, Keshav Kumar Rai. Did they indicate? I guess. No.
Yes, sir.
Yes, 4. Okay, 11. Okay,
Yes, sir.
Sektivel. Okay, Sektivel Propol 11. Sweta 5. Meher Sai, Venkat Meher Sai, and Kushak was 7. 7. 14. 9. Anayakuma 9. Okay, yeah. Just see, okay, the numbers what you indicated. Okay, is it right now? I think what you indicated. Okay, now I'll open the titles. Okay, titles of the papers. So are you able to see a Word document, term paper titles?
Yes, sir. It is.
Okay, so here I listed down, okay, 1 to 14, okay, topics, okay, title papers. Okay, so these, okay, I'll upload, okay, now, okay, to the folder, assignment folder created for the term paper. Okay, so respect to okay, number, okay, you need to pick that paper. Okay, read that paper. Okay, some of them my papers also there which are relevant to this course. Okay, this time I given my papers also which are basically published, which are related to plastic deformation, microstructure evolution. Okay, so these all these 14 papers, okay, are given. Okay, so what you have to do, the guidelines are here. Okay, the whole, I think everything has been mentioned here. Okay, this is about the report, guidelines for the report. Okay, maximum marks 15 marks for the report. Okay, how to, okay, you need to refer, okay, apart from this paper you need to refer at least 5 okay, at least 5 references. Okay, so apart from, okay, so that means actually in your report you should, okay, write down at least 5 more references which have been, okay, connected with the paper. Okay, you need to give, okay, a concise overview of the paper describing the main goal of the others as well as the used methods and results. Okay, if the selected paper, okay, this paper is too long. Okay, highlight the certain aspects, especially interesting major findings, describe these in greater detail relevant to this, okay, course, plastic deformation and microstructural evolution. Okay, and you may have to give some critical comments finally, okay, from the paper. Okay, so there are, okay, negative marks for plagiarism. I think one of my TAs will correct that plagiarism check. You don't need to do any plagiarism check. You just upload the report in PDF format, okay, to the, okay, into the folder in Moodle folder. Okay, in the Moodle, in this class there is a folder term paper. In that you have to upload your report. Okay, so there is already deadline has been mentioned in the first lecture itself. Okay, the deadline is actually 29th October. Okay, by 11, okay, 59 p.m. Okay, that before that you have to submit it. Okay, after that I do not accept, okay, your term paper reports. Okay, so negative marking depending on the amount of plagiarism check, there is a negative marking. Okay, so make sure that you understand the paper and write it what you understood, okay, from the paper. Okay, so these are the okay titles. You can see some other thing, okay, which are actually relevant to this course. I to most of the thing, okay, most of the information. So I had given 14 topics, so 14 titles of the term papers. Is it clear about the term paper report? Okay, you can't change the title. Okay, whatever number you got it, okay, the corresponding number paper you have to pick up.
Sir, on Moodle, the due date is given as 21 September.
That is for the assignment.
Okay,
Assignment
okay,
one.
okay, okay.
Okay, term paper one. I just I'm creating now. Okay,
Oh,
what I say, I'll create a folder. Okay, term paper folder. There I'll upload these titles. Okay, and along with the Excel sheet numbers. Okay, your selected numbers.
okay. And sir, 5 extra references means we have to cite 5 different papers, like
Yes.
apart from
Yes.
this paper.
Apart from what you are reading, okay, that should be relevant to your okay that paper. Maybe some back references are there, okay, because each article will have some references.
Yeah.
Okay, you must read at least 5 okay important articles out of those references.
Okay.
Okay, I may ask questions from the reference also. Okay, you cannot take random look at those references. If you're okay,
So,
Then
so it has to be at
10
least
and
5.
at least 5. Okay,
At least
that
5
means you
references.
must read. Okay, apart from this stuff, you must read 5 more papers.
Okay. Okay, sir.
Yes, one more, somebody is asking. Sweta, or
sir,
somebody is
both
asking.
team members need to submit report or one
One
report
single
is
report, one single report, one single report. One single report,
and
both of you are going to be awarded same marks, okay? Okay.
and report no need to submit, sir. I mean
No, no, one student
PPT,
together. One
PPT.
student. PPT, I'll come back to PPT later, okay? Okay, this is about the report. This is about the report.
Sir, minimum how much plagiarism is accepted?
How many?
How much plagiarism percentage is accepted?
I said 25%, okay?
Okay, sir. Okay, sir.
Yeah. Okay, 25 onwards, okay, starts negative, okay? Marks. Okay, the report has to be 5 page, okay? I think, see, given, okay, 5 pages should not okay? The text including abstract, okay, figures, everything should not exceed 5 pages.
Sir, could you explain the plagiarism 25% thing which you just said? Because these are
Sim-
papers which we are going to be copying, not copying actually, like understanding and making our own view out of it. So
yes,
25% plagiarism means what, sir?
it's similarity index, okay, because from the paper, for example, you cannot copy text directly, okay, you have to
Okay,
whatever understood you have to write it, okay, in your okay,
okay,
understanding of, you cannot pick directly sentence to sentence like that, okay,
okay, okay,
you should not pick the sentence directly as it is, okay.
okay.
The text, okay, can be 5 pages, okay, all figures, okay, must have, okay, 4 figures are allowed, okay, this can be separate out, okay, okay, this apart from the text we can have 4 figures and maximum 2 tables, okay. Is it clear? Any more doubts? Because I had given all the details here, okay, you can just simply follow for only for report, okay. Presentation thing I'll come back after midsem, okay, because I want to give some time to read the article, then I'll come back to you about the presentation, okay. Said, okay, read the allotted paper thoroughly, understand it. Each team has to prepare a common report. But both of you submit, okay, in Moodle. Same report, and so both of you, so that mark is easy for me to give marks, okay. Same report can be submitted, okay, by both the team members. Any more doubts? Is it clear?
Yes, sir.
Yes, sir. Everything is clear.
Okay. So, okay. I think this Friday we don't have class, being a holiday. Okay. Then you will be having your midsem week. So we'll meet again on 22nd of this month. Okay. So we'll be having exact 2 weeks gap. Okay, from now. Okay. So I think I took 10 minutes extra time today. I think just yeah. I think you won't mind it. Okay, this 10 minutes extra time. So we'll meet again on 22nd September. So before that, you need to submit assignment. Okay, 21st is the deadline. Okay, for the assignment one submission. Okay, so I'll stop recording now. Okay, because I think it's going undergoing. Okay. I'll stop recording because all this information is useful for other students also. That's why I recorded up to this point.